We are live. Good morning.
Good morning, Alex.
Good morning and welcome. Thank you for joining the webinar. We are going to start soon, but while we wait for the last participant, let me introduce you the itinerary. The meeting is divided in 3 sections. In the first one, Stuart Maddock, the Technical Sales Manager of HiRef UK, will introduce the system known as water loop. Then Eduardo De Panza, Managing Director of Acquaria Ltd, will talk about the water loop heat pumps. If you have any question, you can write to live at webinarweb.co.uk. So in the third section, Stuart and Eduardo will answer you. We will try to reply to all of you, but if we don't have time, we will answer you in the next days. So I think we can start with the first presentation. So let me introduce you Stuart Maddock, and I'm sharing your screen, Stuart, and so we can start with your presentation. Okay.
Okay.
Up to you.
Morning. Right. What we're talking about this morning is the high-rise buildings and water loop systems. Water loop systems, it's not new. It's been around since the early 1960s. The system was developed for commercial and retail sector and has mainly been used for that for many years up until the recent realization that with high-rise buildings for apartments, it could be used from the shopping malls and offices and could be used successfully with the apartments. Now, with the buildings, you can look at the water loop as a district system or as a local system. The local system really is, with what we're talking about in this instance, is the building itself. Because when you look at the district buildings, the district heating, you have an energy source or an energy center, and then that's shipping in water to the various buildings around the locality. But the problem is that if you've got a district heating system, it all relies upon one area. So if there's any problem, it affects many buildings. If you have it as a localized system, there's the controllability for that one building itself, and also in how efficiently it operates. So by having that one building, you're looking at controllability. Now, in the past, you had it as an office building with a Tricooler on the roof, so it was cooling the loop down. But when you look at the Tricoolers, you had to put heat in as well, so but the boilers were in the basement. And the units themselves in the offices and shopping malls were themselves heat pumps. And so you had a system which was controlling the loop, and you had separate heat pumps for the shopping malls and the retail areas. This is something that can be utilized in the future for mixed usage of many of these high-rise buildings. Now, if we start looking at the Tricooler, sorry, that's removing the heat, which is on the roof of the building. The heat from the loop itself means that you'll need to add in heat to that loop to control it. Why I say that is that the loop itself has to control within certain temperatures. And normally you're looking at it controlling between 18 and 30 degrees. But it gives you all of that inertia. So when you've got that water going around that loop, you've got inertia for a long period of time, depending on how the loop is sized. Now, as I was saying, in the past, the water loop was had a heat source, which is normally a boiler, and some form of rejecting. But what you're doing is replacing the boiler, which was normally operating at 60 or 70 degrees, with a heat pump. So you end up with a simplified, very much a simplified system. This has problems because of the water flow that you can get through a heat pump. So you have to consider how that is going to be thought about. Now, heat pumps in general operate in the opposite. So if you put in heat or taking heat out and put it into the apartment or office space or retail space, it means that you are then pushing cold water into the loop. And so you have to consider how those opposites work. So as you're heating up the apartment or retail spot, the loop is getting colder. And so you have to put heat into it. And so you end up with a system which is injecting heat or rejecting to keep this neutral water between ideally 18 and 30 degrees. And so you end up with a number of heat pumps working with heating or cooling in an office space and retail. Because of diversity around the building, that can help because you have in certain areas, some parts are cooling, where in the other part of the building, it's heating. This is slightly more of a problem when you come to apartments, because you're looking at domestic hot water as well as the heating of an apartment. So apartment requires more heating than the office and retail. And so could be an imbalance. So in some ways, you need to think about how you can recover some of the energy which you would be rejecting, and being able to use that further down the line. Because of the amount of water which can be in that loop, you don't always have enough inertia. And so you need some sort of water storage that can hold hot or cold water to smooth out some of the problems that you have with the imbalances throughout the system. Because if everything is in heating mode, you can get a problem where the loop itself is getting colder and colder and could get to a point where it could freeze. Now, the advantage of the loop itself is that because you're operating between 18 and 30, it can be made of plastic pipe, or which is cheaper than galvanized or copper pipe. But the problem is that because it's not normally insulated, you can't go too cold, otherwise you can get condensation problems. And because of the lack of insulation. And so you have to be careful about when you're going to introduce heat and how much heat you're going to put in there to keep that temperature above the minimum temperature of 10 degrees. And you should be operating really at 18 as the minimum to enable you to stop that freezing and condensation that could be a problem. The water loop itself, as I say, is a reservoir of energy. So depending on the type of material used for the water loop, the maximum velocity and the pressure drop has to be considered, because if you're using plastic pipe, it has a different characteristic than using copper or galvanized steel. And there's evidence to say that the pressure drop is less, but is probably more restrictive because of the strength of the material. The other area to consider is when these have been operating for 10, 15 years, the cleanliness of the pipe internally needs to be considered. How is the water treated? How is the system operating? Otherwise, you can get the algae and slime buildup, which in the heat exchangers that, especially on small apartments and residential equipment, as well as the retail, you can get blockages within those plate heat exchangers, and they need to be flushed out. They need to be cleaned regularly to ensure that they are operating, because otherwise you end up having the minimum water content missing, and the water flow through those systems, and the efficiency starts to reduce. Now, the other thing to consider is that the loop itself, is it going to be a constant flow or is it a variable flow? If we put in a heat pump in, they could operate on variable flows with variable water temperatures from the heat pump. But the load itself, the apartment unit or retail unit, would need to have a bypass if it was fixed flow. Now that bypass gives you more of a problem because of initial setting up and initial commissioning. And then you've got maintenance of that valve as well. So the variable flow eases that situation because you only start using a two-port valve to stop or open to put water through the apartment unit. And it also ensures that you've got an efficient system, because the pump will start backing off when you have units in the apartments shutting down because people are not in the buildings. And so it gives you a lot more flexibility with the variable flow. But because you've got variable flow, you need to think about the minimum flow that can operate for the heat pump itself. So you have to consider the bypasses, and then you have to add in the control of the pump itself to think about how that pump and the differential pressure is looped back to give you feedback situation. This needs to be considered because you could have many of these apartments with units switched off because people are on holiday, or they're not in the building for a certain amount of time. So the other part of that is the minimum load needs to be checked against the heat flow load as well. Because through a heat pump, you need to have a minimum flow for them to operate. If you don't have that minimum flow, they will start to create problems in cooling and in heating. Now, the other side of this is if you have a heat pump, and the reason why Tricoolers were used to begin with, excuse me, I'll just take a drink, was because the weather conditions enabled us to have free cooling. And so a Tricooler on the roof was very useful for energy, because it's the minimum way of cooling the loop down with the minimum energy. So in that respect, they were ahead of their time, because they were always thinking about the energy usage. But free cooling, we should be considering. And especially when you consider that if we're operating at 12 degrees, how many hours per year we think about free cooling, and it's possible to free cool. If we just look at a London map, for example, of a number of hours of against temperature, you can see that free cooling is quite beneficial. And then you've got the mixed condition as well, and then the mechanical cooling needs to be put on top of that. So it needs to be thought about how you can look at reducing energy down, because if we're talking about a heat pump, we need to be thinking about not just utilizing it for heating or for cooling, but how can we utilize it for the mid-seasons or in the colder temperatures. So the Tricoolers may still have a role to play within the areas. But if you're looking at Tricoolers themselves, they're quite large, and so to take the load in. And so you need to think about the combination of size against maximum amount of efficiency. But because they are in the cold weather outside, they normally need glycol in the system, and so you need to decouple those from the water loop itself, which creates another problem in that you've got a 3-degree differential between the what you can get outside and what's on the water loop itself. And so you have to consider how you're going to, what temperatures you're going to operate the loop at to make the efficiency of the loop work. If I were to talk about the indoor units and what temperatures they can operate at, but it needs to be thought about to maximize the total efficiency of the system, because we have to think about the system itself. And so if you look at the a Tricooler, you would either go direct through, so you can't put glycol in unless you're putting it through the whole system, which is then making a problem, or you put it, decouple it through a plate heat exchanger, and then end up with a variation in temperature between outdoor and indoor loops. So your primary and secondary, there's a differential of around 3 degrees. If we start looking at the products themselves, you can then think, well, just cooling the loop down without thinking about the heating side, you've got free cooling chillers. So you can look at having the cooling the water down through the free cooling mode, and then the mechanical cooling coming on to ensure that you're staying within those temperatures. And the higher the water temperature, the more efficient the free cooling system is, and and also the chiller itself. But there's two types of free cooling. One, sort of same with the Tricooler, where you've got glycol in the water loop system. So you end up with a water going through the free cooling coil and then coming back through the heat exchangers and then the air goes through the free cooling coil before going through the refrigerant cooling coil. So in different formats, you have it's mixing at certain areas, and you can get partial free cooling, and enables you to look at how the free cooling is. But then if you want to decouple the glycol from the water, you've got to put a heat exchanger in between the water that goes to the free cooling parts of the coil and the water loop itself. And by doing that, you again have the same problem as with the Tricooler, and have the 3-degree differential with the water and the from the loop itself and what goes through the free cooling coil. Then you have what else can bring that cooling down. And of course, you can use adiabatic. It's used a lot on the continent for steam into the, showers into the area to cool the spaces down through the adiabatic technology. So this can be utilized for a dry cooler and also for a chiller. And so you can reduce the size of the dry cooler, but also reduce the size of the chiller as well. And the so, for example, you can take it from 35 degree 20 volt down to 20 degrees saturated before it goes through the chiller or the dry cooler. And so you can, instead of having a large coil surface, you can reduce that coil surface down. But with the introduction of water, you have to consider about the water usage. And it's something that we think about in how you can benefit against the water usage. And in some areas, you can't use water to cool these certain dry coolers or chillers down further. It depends upon the planning areas. But the wetted mats and other areas are very effective. Then we look at heating. Now, when you look at the chiller, you just put a reverse cycle in on the refrigerant, and you can get heating out of one unit. So with normal refrigerants, you're looking at water up to 55, and in some cases you can do 60 degrees. But to go higher than that, you need to start thinking about other refrigerants. And this is where the cost and R&D start to come into play. But these units, as you can see, it's an air source heat pump, and so it's external. And so it needs to be thought about where these can be sited. But the other thought that you need to think about is the deadbands with using the heat pump, because you've got to think about when the compressor starts, how long it goes for, and when it stops. And this is the same for a chiller as well. And so if you don't have that deadband in place and you have too many stops and starts, it can cause a major problem. And you can break compressors. You can also freeze up the shell and tubes and plate heat exchangers which are in the systems. And so to stop the short cycling, we need to think about buffer tanks. So you need to look at the minimum water loop capacity against the chiller or heat pump minimum capacity requirements. So there's two things there. One is the flow through the chiller and heat pump, but also minimum volume. And minimum volume is often neglected. And to keep the heat pump or chiller operating for as long as possible, you need to think about the buffer tanks. Now, these can be quite large when if you've got a large system. So you could have up to 6,000 litres or even more. But because you've got a heat pump, you could have two, one for heating, one for cooling. But if you don't have that in play, and the chiller and heat pump is jumping all over because you've got to control the area, but also you have that deadband between cooling and your heating side. So you have to think about the critical part of when it's heating and when it's cooling. And the buffer tank is important to ensure that you reduce the critical areas and bring the temperatures within the 18 to 30 part for the water loop. The other solution is to think about a multi-system unit. Now, multi-system is a bit more unusual in that it can, instead of a heat pump either heating or cooling, you can blend them. And so using a refrigerant cycle and pumps on the hot side and on the cold side of the evaporators, you can ensure that you can balance out how much heating, how much cooling. So you end up with a variable unit. So instead of where with the heat pump, you've got to heat, switch off, turn it off, and then it goes on to cooling and then comes back on again. And so you end up with that deadband. But with the multi-unit, you can be cooling through the heat exchanger for the cooling side, and so the refrigerant side is going through and it's rejecting out the air to the atmosphere. When you look at the and you want partial recovery, you have part of the refrigerant cycle takes it through the 3-port valve and into the hot water heat exchanger. And in this case, I can't do my maths, so it's got 90 and 20. You're normally looking at 80 and 20 and rejecting the other heat which is not required. So the 20% of heat not required, you take it out through the through atmosphere. Now, as you are increasing the heating and reducing the cooling down, it starts to become balanced. And although you're then looking at your rejection still through atmosphere, you're reducing the amount that you're rejecting. And so it's a variable area until you get to a 50-50 and there's no rejection through the heat pump to atmosphere. And you've got a balanced system, 50% heating, 50% cooling. And then going the other way, you can go onto heating and you reject what doesn't need to be cooled out. And so you're gradually taking it out until you can get to 100% heating. Now, this is very useful if you have an unbalanced system. And also, if you've got heat pumps, you can top up your buffer tanks and other areas on your water loop. Now, the problem is that when you've got units outside, you've of course got noise problems. Now, the noise is generated from the compressors as well as from the fans. When you had a dry cooler, it was only just the fan noise. But of course, once you put the compressors into a heat pump, then you have to think about how much noise external. So there's other ways around that, which you can go to a internal air to water unit, and these can operate the same way with free cooling for the cooling, heat pumps, and also multi-systems like I showed you just earlier. So you can have your 2-pipe and 4-pipe multi-system. And you then have a radial fan which draws air into the building and out again at either low level or partway up the building, or a mix of both, depending upon where you can put your plant room. The other option to this is a water-to-water unit that's using, instead of refrigerant to move the hot and cold around, you can use the another hydraulic type system. Now, with the indoor units, you can get these in 4-pipe systems, or so you can use them as you would, but you've got to then reject the hot water or cold water at some point, because these are internal, and so that they can be kept in the basement, or just 1 floor down from the roof itself. But you can have a unit which is a hydraulic unit, which then has the pumps and valve sets, which you'd normally put into the multi-system, the multi-unit. And so with that Polymorph unit, it can be set up to heat the water loop, to cool it. You can use the Tricooler as a free cooling system, but you can also reject either the heating or cooling side. So it's a useful unit which can be hydraulically used to operate the same as a multi-system. So to give you an idea, I've just put a few schematics together of the unit itself. And if you've got a 2-pipe system, it complicates it in the way the pipework operates because of how you're transposing water around. And then, of course, you can go to the 6-pipe unit, and then it's easier from the chiller, using a chiller, standard chiller, because you're rejecting heat, you're putting cold water, and you've got cold water at the same time, and it's moving that water around to enable you to utilize where it's going. And with a standard chiller, then you can end up with a free cooling facility, as well as heating your source. So it has that benefit. Now, the calculations from a system, there's so many variables. I could spend probably an hour just going through all the calculations of how you do this. There's many variables, and the best way is to have a system and then go through the best calculation and the best system itself, either multi-system or a standard heat pump or a combination of all the ones I've just shown you, to be able to give you that the highest energy that you'll get out of it at the minimum, so have very high COPs. What's the future though? The principle is there, but if we're using heat pumps and how we're looking at it, There's also the refrigerant side. So yes, we can use 1234ZE, which gives you GWP of 6 on our chillers and heat pumps. But from then on, you need to start thinking about CO2. Now, CO2 heat pumps, we've developed a range of CO2 heat pumps. They have pluses and minuses. At the moment, it's considering how we get the temperature differentials to operate within water loop areas. This is something we're working on with the project at the moment, and it's interesting. It can be used, but because of the normal operation of CO2, you're looking at 40 or 50 degrees centigrade differentials. But there's ways of harnessing it, and this is, as I say, for development, which is how we're looking at it and how we're looking at the efficiency, especially when we think about how the water loop is going to operate and all the variables, because there's many variables. So is there an ideal unit to control the water loop now, in the future? Well, you could say a free cooling heat pump, whatever that is. It's a Tricooler with heating and cooling, or a multi-system with free cooling. It's something that there is not one to fit all. It needs to be thought about what the system is, because these systems are variable. And so it needs to be considered what is right for that particular building and that system to maximize the energy usage. So in conclusion, we can get high overall efficiency of the water loop itself and just controlling the water loop, and then it's thinking about what's connected to it. And if you, in the past, when we've connected units for office and retail, they've been very efficient systems. Everyone will talk about how the apartment unit will be efficient itself. But a water loop is scalable. There's, because it's scalable, you can size it for the overall building, but it can be, as the apartments become, or the floors become used, you can build on, and especially if you've got variable speed systems. It can be also used for many applications. And that is important because many of the new buildings that are coming into play and thought about now have residential at the high levels, but also at the lower level, you've got retail area. And so you need to consider that how all of those buildings come together. And so we can provide maximum efficiency with maximum comfort, but also because we've got all that part load availability and that inertia that you've got on the water loop itself, you can, with the variable system, you've got maximum part load efficiency. And that's the end of my parts, and so thank you for your attention.
Thank you very much, Stuart, for your presentation. And then let me introduce you, Eduardo De Panth, with his presentation. Hi, Eduardo. Hello.
Hi.
While we wait for you to share the screen, let me remember that for any questions and comments, I invite you to use this email. I showed you the email, We cannot manage the live chat and the comments, so please use this email if you want to ask something. I see that your screen is ready, so I share the screen, and it's up to you.
Thank you, Alex, and thank you, Stuart. So basically, yeah, can be seen, yes. So basically, we have seen from Stuart and from HiRef how to, let's say, manage the control of the loop and how to control, let's say, to keep the loop under certain operative range. Let's have a look now on the other side of the loop, the user side. And we will see that in each apartment we are proposing a single heat pump, a water heat pump. And in the next few slides we are going to show, let's say, the characteristic of this heat pump, some performance and operative benefits of this unit, and then at the end some installation and service and maintenance interesting benefit that we believe, especially for this kind of application, are quite strategically important. So here is the scheme. So basically, in each apartment there is a heat pump. Obviously, when the heat pump is working, is operating in heating, it's let's say extracting heat from the loop. And when the unit is working in the cooling mode, it's reversing heat into the loop. So potentially there is, especially during the mid-season, there is the possibility to have an energy balance within the loop when some units are working in cooling and the other in heating. But there are also two more, let's say, interesting area, especially during the summer season, where there is a great benefit in this structure. For example, if during the summer season some units are working in cooling and other units in the building are working in domestic hot water production, in that moment these two different settings are balancing, giving let's say zero contribution into the loop. And the second situation is, again, during the summer, if one unit in a single apartment, one unit is working in cooling, and at the same time is requesting the domestic hot water production from that unit, that unit is working with a zero contribution to the loop in that very moment, because producing cooling, you can have domestic hot water, let's say, as a free energy. And we are going to see later how does this works with also a calculation example. So this is the unit. Basically, it's a 600 by 600 by 2 meter high unit, and this it's available in two sizes. For example, heating and cooling, 6 and 10 kilowatt of nominal capacity. Obviously, because there is an inverter compressor, there is a range, minimum and maximum. I give you here 3 working points. Okay, the standard as a reference is the 14511, but I give you here as a working example 3 different working points. In heating, 30-35, typical for underfloor heating, or 40-45 in case of fan coil, and on the loop side, 20-17. And one cooling condition that is, for example, 712, typical fan coil, and 25-30 on the loop side. In this case, we can see that the heating capacity is roughly 7 and 12 kilowatt for both, let's say, combination, roughly, with a COP of 6.5 in case of underfloor heating, or 5 in case of fan coil. And the cooling is 4.5 and 7.7 cooling capacity, with a COP of 5.2 and 5.1. Obviously, we appreciate the fact that in the UK, especially in the UK, the only heating version is still it's still an option, especially so if you are considering, if you are choosing as a system the radiators. So also the only heating version is also available. So this is the unit. The unit is fully accessible only from the front side, so not from the side or from the back. So when you open the front panel, you can see the tank, the 160 liter, 65 liter tank. This tank is for system hot water, so it's not domestic hot water. It's a 165 liter fully dedicated of technical water, fully and exclusively dedicated to the domestic hot water production. So the domestic hot water is being produced by an external heat exchanger, external to the tank, but inside the units, obviously, so that the domestic hot water is being produced instantaneously when there is the request. This is given the fact that in this case, the tank doesn't need to be brass certified because it contains only technical water. For this reason, there is no need of Legionella cycle. And this is also given the guarantee that the domestic hot water amount is really reduced at the minimum, and there is no contamination between technical and domestic hot water. The tank is standing still in any case, and let's see the next how it works. This is how it works, the domestic hot water production. So basically, this is a simple operative cycle of the domestic hot water. As you can see, the tank, there is the external heat exchanger. When there is the request of the domestic hot water at the tap, the pump, the variable speed pump is activated, producing instantaneously the domestic hot water. The pump is regulated by the temperature on the outlet of the heat exchanger. So as you can see, all this, the components within this gray area are brass certified. So the pipes, the pressure inlet regulator, the blending valve, and of course the heat exchanger. But not the tank, because the tank is containing only technical water. There is also a backup heater as an emergency. So this backup heater is not working during the normal function of the unit of the domestic water production, but only in case of emergency. In any case, the Legionella cycle can be implemented, can be activated for service reason if there is the request, but not for the normal functioning of the life of the unit. So this is the in the tank we have typically 55 degrees in order to have 50 degrees at the outlet of the heat exchanger, and then in order to have 48 degrees at the tap, as per the UK regulation. The next working function is, this is the heating mode. And I want to show you how it works, because it's quite interesting. Because as you can see, when there is a space heating request, that can be underfloor or can be fan coil units or radiators, you see this is the compressor. So the compressor is sending hot gas through this heat exchanger that is not activated because the pump is not working. So the hot gas is going through the four-way valve to this heat exchanger. So there is a dedicated heat exchanger only for the space heating. And after the expansion valve, the gas is evaporating on the loop side. So I'm reversing to the loop some cool energy, let's say. If in this situation there is a request of the domestic hot water, that can be done simultaneously because there is a dedicated heat exchanger for the domestic hot water. So the two can be done simultaneously, independently. If during this there is the temperature inside the tank is decreasing, so the thermostat is giving the consensus to the system to be replenished. In that case, this pump is activated. So in this case, the first heat exchanger is extracting the first part of the gas, working as the superheater. And then the other gas is going again through the four-way valve, again to continue to produce space heating. So in this transitory situation, we can have together and simultaneously space heating, domestic hot water production, of course, and domestic hot water tank replenishment. because in this transitory, the compressor, of course, is increasing a little bit the speed, and also the system is managing the two variable pump accordingly in order to have to share the energy between the two heat exchangers. And then, of course, on the source side, I'm reversing some cooling energy. That's the heating and the domestic hot water. By the way, there is also eventually a backup heater also in line on the heating supply. Again, this is not working normally. It's just an emergency in case of failure. This is the heating mode. In the cooling mode, in this case, the compressor again is sending the gas through this heat exchanger that is not activated, and then the reversing valve is sending the gas on the loop side. So the loop heat exchanger is working as a condenser, and then after the expansion valve, this is the evaporator, and so I'm producing a space cooling. It can be for underfloor cooling or for the fan coil. Again, during the cooling space cooling production, I can have simultaneously domestic hot water because there is an independent and separate heat exchanger. Interestingly, if in this situation I have again the consensus from the tank to be replenished, in this case, when I activated this pump is extracting all the gas from all the heating from the gas. And also excluding this, closing the two-way valve on the loop side, I can really let this heat exchanger become like a total heat recovery exchanger. So basically, in this very moment, I'm recovering all the energy for the tank replenishment. The domestic water request is still working to produce hot water, and I'm producing a space cooling from this side. So in this very situation, I'm not reversing into the loop any energy. So it's like to have while I'm producing space cooling, I can have free energy to replenish my tank. So in this situation, the efficiency of the system is very, very high. And I want to show you in the next slide, like a simulation of this. So this is a formula, a simple formula we created to explain this. We call total energy ratio. Let's say if we calculate on this situation, the cooling capacity plus the domestic hot water capacity in the tank replenishment divided by the power input, and we call this total energy ratio, we can see this here two examples. For example, 712 on the cooling side, or 2318 in case of underfloor cooling. So underfloor cooling or fan coil cooling. And on the let's say domestic water side, 5055. In this situation, we have a cooling capacity, for example, on the fan coil of 3.36 kilowatt and a ER of 2.2. The efficiency, of course, of the cooling in this case is very low because I'm condensing a very high temperature on the other side. The domestic of water capacity in this one is 4.89, and the COP is 3.2. So the total energy ratio in this case is 5.4. For one unit, 5.3, or in case of underfloor cooling, it's almost 7. So as you can see, the overall efficiency is very high. This is not a COP. This formula doesn't exist in any standard, in any certification. It's just a way to give an operative, to explain an operative efficiency of the system. In this case, the overall efficiency is very high, but also we are not reversing into the loop any energy. So it's a double effect of benefit, if you want, in this special operating mode. And the last operating mode is domestic water production only. So if there is any request of space heating or cooling in that moment, the units can work as, let's say, independent domestic hot water production. Can be, again, only at the tap for using the instantaneous production, or also as a tank replenishment. So in this case, the tank heat exchanger is working as a condenser, and I'm evaporating on the loop with some cooling energy. Obviously, in this situation where there is no space heating or cooling demand, the system can optimize the COP during the tank replenishment mode, modulating the speed, the compressor speed or the pump speed. That was the operation. From the installation point of view, interestingly, these units can come with an interesting manifold as an accessory, in a way that when the apartment is still under construction, I can install this manifold and I can connect all the piping, and then only when the apartment is ready and finished, I can bring on site my heat pump, and easily I can fit through the door, of course, and line up connected piping, let's say, flush the system and take the air out, and the unit is really ready to be operative. So very, very quick and easy to install for a peace of mind of the construction company, but also of the installer. And the second benefit is from the service and maintenance point of view. As you can see, all the refrigerant components of the units are included in this refrigerant box. So it's also a meaning of double installation, but mainly for a quick, let's say, dismantling. If you need to service the units or to make some intervention, you can easily unplug the electrical cable on this position. You can unbolt the 6 piping that are on the front of the units. You can easily extract the box and take it to the service station to make a very quick and easy installation, repairing or service of the unit. Also, in case of, for example, if the owner bought, for example, the only heating version, and he wanted to upgrade with heating and cooling, he can just replace the box and not the unit itself. And finally, I want to show you just a couple of interesting accessories of the units. One is the flow meter that we give as an accessory here inside, let's say, on the loop side, on the outlet of the loop side, because this accessory can be very interesting for the commissioning of the units, of course, to check the correct flow on the brine and loop side, but also during the operation of the units, because it's important to keep to monitoring the flow on the loop side to avoid any issue on the compressor side. And the second one, this flow meter is also very, very interesting, because the measure of the flow on the loop side, on the water flow, together with the delta T temperature on the loop side, can give an important information to the building manager to charge the tenant or the owner of the apartment for the consumption of the loop energy. And this is quite interesting possibility. And the second one accessory is the two-way valve again on the source side, because it's important to for example, to shut down, to close the loop flow, for example, in case of domestic water production together with the cooling mode, or for example, if I leave the house for holidays for a few days, I may decide to shut down the units and the flow to avoid the loop flow through the heat exchanger, to avoid the consumption of this energy, let's say. So that was I think the last of my presentation. So thank you for your attention.
Okay, thank you, Eduardo. Let's go also. Okay, here we have also Stuart. So let me see if we have time. We have some questions from the audience. But before going on, let me remember that if you joined the meeting in late, we will share the link so you can see all the meeting, all the video in the next days. Okay, can we go on with the questions? I remember that we have this email available for all the questions, and it will be available also in the next days. So if you want to ask some questions, you can use this email also in the next days. I go on with the first question, Eduardo. It's okay. The question is, R410A refrigerant is on the phase-out process. Which gas are you using in these units?
Yeah. Well, first of all, 410A is not in phase out. 410A is in phase down, so it have to be reduced. Been reducing, but it's not in phase out. In fact, I want to remember R32 is not the definitive replacement of 410A. It's probably a temporary alternative. It's a flammable gas that is being used as a temporary alternative for 410A. In our units, we are using 410A. Period. I mean, R32, it's fine. We just don't feel confident to place flammable gas inside a residential indoor application. I mean, R32 is perfectly safe. It's perfect, comply with any standard. It's just in this moment, because 410A is still available and can be used. We don't see the reason to force, the situation to use, 1 kilograms of flammable gas inside our units. So that's our choice. Obviously, in the future, we are monitoring the situation and we will make some changes. At the moment, is 410A.
Thank you, Eduardo. Stuart, a question for you. What are the benefits to have a loop at mild condition temperatures?
Mild conditions. Well, the main reason is because you're not introducing extra temperature within the building itself. By keeping the loop between 18 and 30 degrees, most of the pipework usually goes down corridors. Those corridors get overheated, and so you would come out of your nicely tempered apartment and find that the corridor is far too hot. It might be nice in winter, but in summer temperatures, it can be overbearing. And so you need to have extra cooling in those corridors, which is extra energy.
Yeah, cooling is not a real demand in a residential application.
Well, that's subjective, really, because if you're buying an apartment which has high solar heat gain, and the ones which are above you may be more expensive in their fit outs, so that they have the cooling facilities available to you. It's not, you're there suffering with all the heat in that apartment, and not having the benefits of especially when you've got a system, as Eduardo has described, of being able to cool. And so it comes down to the capex side of it, and maybe Eduardo can enlighten us on that, where you've got how much extra it would cost to have a indoor unit, apartment unit with cooling as well as heating when it's built for that.
I see.
Yeah, well, absolutely. Yeah.
Eduardo, another question. I have another couple of questions if we have time. Nobody in the market proposes simultaneous production of heating and domestic hot water. How and why can you do it?
Well, yeah, that's an interesting question. Well, I would say because we have done a good marketing, to be honest. I mean, it is true. It's not so common, but in fact, I want to say when if you want to develop a new heat pump, and you want to make an innovative heat pump, you should think about the end user needs. You know, I mean, everybody we have a gas boiler, or we had a gas boiler. Gas boiler can be also noisy and sometimes failing. So when you design a new heat pump, you should not try to compare a gas boiler. You should do something better, and you should think about the end user needs. Now, if I'm producing heating with my heat pump, I don't want to have to stop the heating because I have to make shower, and vice versa. So in doing this, you have to think about, and then you say the solution is quite simple. You need to use a dedicated heat exchanger for each of these needs, and do it. I mean, it's not more expensive. It's just smarter in making and in designing a unit with this benefit. So yeah, I quite feel that this is quite innovative heat pump from this point of view. Yeah.
Okay, the very last question, because we are late with time. As the apartment unit is set up for cooling, will this mean that it would be economical to install this unit as a standard to cool lower cost base apartments?
Well, that's an interesting question, because as Stuart said before, cooling it's a real demand. It's a real demand, especially in the UK, especially in London and many other cities. The point is, when we make a price comparison to choose the system, especially in new build, we should, in my opinion, we should compare. Two different things. We should compare not only capex expenditure, but also running costs. First things. And second, we should think about not only heating, but heating, cooling, and domestic hot water. If we consider this, we can see that cooling is essential. We can see that basically a system like electrical radiant panels or radiators, they seems to be the cheapest solution, because you consider only capex. But if you consider also the running cost, including also heating and cooling, they are not the cheapest. So especially radiant panel with the COP 1 or COP 0.9, they don't fulfill the energy efficiency request. Radiators, they don't fulfill the running cost request, because they are running water at 55 or 60 degrees. That is more expensive to produce. So if you consider the two together, running cost and capex, and heating and cooling and domestic hot water from the other side, you can realize that maybe you have a unit that you're producing cooling and domestic hot water for free. So in this situation, in my opinion, a two-pipe fan coil system or underfloor heating and cooling, these are probably the overall most efficient and cost-effective alternative as a system solution. That's my overall opinion.
Okay. Thank you, Eduardo. I think, do you want to answer? There is maybe other questions. Maybe we are late, so
in any case, we are going to reply to all the other
Yeah.
questions coming in the next few hours or few days. So no problem. We can reply to anybody. I think Stuart.
That's the same. Yes, we can reply.
Okay, so I remember you that the email is available also in the next hours and the next days. So if you want to ask some question, you can use it also later or tomorrow or in the next days. So thank you very much to Edoardo and Stuart. Let me remember that we will share the link to see all the webinar in the next days. So if you lost the first part of the webinar, you can join the link and see the whole webinar. What say, Edoardo, Stuart? Thank you very much.
Thank you, Alex. Thank you, Stuart.
Thank you, everybody, and see you soon. Bye.
Thank you very much. Bye.
Bye. Bye.